as I started saying, kind of Siggy just demoted me to a junior test trainee. You promoted me, sorry. You promoted me from a junior developer to junior test trainee. So yes, I am a junior tester. I'm a junior developer, a senior developer, a product owner, the key support person, and kind of everything else in a single person product. I started building it as a side effect of me not traveling that much when kind of COVID started. I kind of decided that making more children is probably not a good thing to do because we already had a +1 during COVID, and then I had to do something else. So I built this product, and the product's taken off reasonably well, and I'm really proud of it. Last month, I had more than 1 million video and audio files being built on the system, and with kind of about 250,000 different people. And I'm supporting all of them myself, and plus I'm building the whole thing. So, and doing that has really opened my eyes to how we need to, or how I need to be effective to be able to achieve that scale on my own. And looking at how do I control things that are not necessarily even understandable to me. And I want to kind of give you a couple of ideas that were useful to me. Maybe you will be able to take them and apply them in your process. We are going to be very far in the kind of meta land for this. The thing I built kind of helps people who are not video professionals create videos very, very easily. And it kind of, for developers, potentially interesting thing is you take a markdown like this, and you mark up, this is a screenshot, this is kind of some segment from some video file, and I want to render some markdown on top of a video or kind of generate it, and it uses realistic text-to-speech to provide voiceovers. And there's a ton of complexity there, but it was incredibly fun to build. And trying to figure out how do I even kind of control this space and figure out, am I building the right thing? Am I building it the right way? Am I testing it correctly? And things like that led to a ton of automation. And I started reading books about kind of control systems and automation and things like that. And one of the books I read that really kind of blew my mind was called The Dream Machine. It talks about the early origins of computing. It's a wonderful history book to read. It's kind of, you can learn how and who and what and why and when, moved from wires to transistors and lamps and stuff like that. And one of the kind of really interesting questions that they were asking in the book at some point is, when people started really kind of looking at electronic automation, that was caused by the Second World War. It was caused by the Second World War because everybody's trying to upend everybody else. And WIENER and BIGELOW were designing kind of anti-aircraft control systems. There was not enough kind of anti-aircraft control personnel, and they were trying to automate that. And one of the questions they were asking is kind of, how do we create a system that kind of maps cause and effect if the effect is kind of in the past from the cause, or if the cause is in the future? So we have an airplane that's going somewhere over there, and we want to shoot a rocket there. Like, so the whole thing is in the future. Instead, like, so, cause is in the future from the effect. So I kind of, I don't know, man, like Marty J. Fox is going to come in a DeLorean and, tell me that I'm my own uncle or something like that. Or, Christopher Nolan, somebody's going to give him my source code and he makes a really confusing Hollywood movie about that, which kind of wouldn't be that difficult because like really confusing is what really well describes my code anyway. So, part of what they were talking about is kind of how feedback systems help people create something that will map out to a cause that's in the future. And feedback systems are everywhere. A thermostat is a feedback system. You basically set it to, 24 degrees. If it's less than 24 degrees in the room, it turns on the heater. If it's more, it turns off the heater. It's a very simple system, very, very effective. Feedback systems are almost everywhere in software. We use them so intuitively that it's great, and unfortunately, my approach to feedback systems was too intuitive. And when I started really researching feedback systems, I found some nice ways of systematizing that and making better feedback systems. And hopefully that's what I'm going to inspire you to do today. So feedback systems, as I said, they really emerged after the Second World War because people started automating things a lot. And then it's about controlling automation, but they're not particularly new. The earliest feedback system I found was from 1600 something by a guy called Christian Huygens, who was a Dutch inventor who was looking to kind of more or less automate the windmills. Of course, fucking windmills, it's Netherlands, you know, there's windmills everywhere. So how does he control windmills at scale and make that easier? And he invented this kind of centrifugal governor where it was trying to measure the distance of the two stones and then going down, going up, so people don't have to press it directly. And one of the most popular feedback systems emerged in 1788, where James Watt figured out how not to kill people with trains by kind of figuring out how to regulate the speed of a train. And he kind of put a very simple kind of centrifugal governor there with two balls, where if the train was going too fast, it would start putting less steam or less water into the engine. If the train is going too slow, it would speed it up. Amazing stuff, you know. People don't have to die that much, and trains can go fast. And so kind of one of the really interesting things why, you know, we didn't get that until the 20th century is there was not much need for that level of control. And people were kind of creating trade-offs in a different direction. And everybody's talking about how, you know, the Wright brothers were phenomenal inventors of aviation, and they created a kind of, the Wright Flyer in 1903 that was totally amazing. But the Wright Flyer kind of, that looks like this, was actually a massive compromise between maneuverability and control. So it was maneuverable, but it was horribly unstable. And that's kind of what they consciously made the compromise, because other airplane designers were designing systems that were stable, but they were not able to get them up and lift them in the air. And the Wright brothers kind of decided that they're going to make something that is, you know, a bit unstable but maneuverable. And you can see kind of this figure here holding a stick in the museum. And it's really, really important because this stick was controlling the plane. And if the pilot let go of that stick, like instant death. And that was kind of a problem with early airplanes. And air aviation didn't really kind of take off in a very literal sense until kind of 10 years later, when a guy called Sperry invented what's called an autopilot. It wasn't called an autopilot back then, but Lawrence Sperry was a son of an inventor, and his father kind of figured out how to use gyroscopes to indicate height. And Sperry was interested in aviation, and he had this machine that his father invented that could indicate height. And he was thinking like, okay, why don't I just like put some, you know, ropes and shit, and then if the plane is going down, just kind of lift it up. If the plane is going too much up, you know, release it. And that was the first autopilot, basically, the Sperry autopilot. It looked like this, and kind of it was so insanely crazy for that time that kind of they actually called it George. It was a human controlling the plane. And this is where, in the Dream Machine, they have this fantastic quote from WIENER and BIGELOW and their colleague ROSENBLUTH, who was actually kind of then taking feedback systems to human, and they said basically through feedback, through creating a feedback system, you could make a mechanism embody a purpose. You could make a plane have a purpose of flying on its own. You can make a rocket system have a purpose of shooting down enemy planes. And now we're getting into some really scary shit here. You know, we have mechanisms that have a purpose. And, you know, Hollywood has been scaring us for years of AI becoming self-conscious and then launching nukes and things like that. But I think kind of, this is a lot more problematic. Imagine your software waking up and understanding what its purpose is. Like, they wouldn't launch nukes, it would just be depressed. It's like, oh, I don't want to come and work tomorrow. Or in Sweden, after launching a sub-process, it could ask for like a month off or something like that. And but seriously, they talk that kind of a feedback system is necessary for a mechanism to embody a purpose. But Rosenbluth was a psychologist, and he was working with them and took this on kind of a bit further. And his idea was that feedback is absolutely crucial for any kind of voluntary action. They were doing research on patients that had these kind of purpose tremors, the problems with kind of the brain, and they were talking about how people that had a miscommunication between the kind of hand and the brain, they would try to pick up a pencil and they would overreach. And then they would kind of try to pick it up again, they would underreach because there was no good feedback there, they could not really control their hands well. And Rosenbluth's kind of estimate was that humans basically apply feedback intuitively, just trying to do these day-to-day actions, and that we can map that to computers to do stuff. So that's really interesting because kind of the conclusion effectively is that you as a human do not have to have all the kind of dynamic equations of physics to figure out if you move your arm at this speed, will it reach it there, and how do you accelerate, how do you decelerate, because that's insanely complex. All you need to do is kind of apply feedback. Did it move enough? Well, let's move it a bit more. So kind of basically feedback loops, the whole idea of feedback loops is they allow us to control stuff that's incredibly complicated with something that's much, 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 much simpler. So I'm kind of, this is a software conference and people are deploying stuff on machines. And let's take a very simple example. So, let's say I have some kind of task queue. The task queue receives tasks. And I have kind of some task processors that can run and process these tasks. Now, the big question is, how many task processors do I need to have? If I have too many, I'm paying too much. If I have too little, then people are kind of waiting in the queue and we're not processing their stuff. And in order to kind of predict capacity correctly, we need to know lots and lots of crazy mathematics. Like, what is the average time of running a task? What are the spikes in demand? What are, the variations between the tasks? What are all sorts of crazy things? And, the whole operating system theory is built on that. But effectively, most implementations of some kind of scaling control system have something that's much, much simpler. What I have is something that kind of measures the number of tasks at the end and says, oh, do I have any pending tasks? Let's start another service. Do I not have any more pending tasks? Let's shut down the service we have. So we don't have to kind of be perfect modeling this complicated stuff. If we can create a relatively simple process that can control it and close the loop. That's kind of the critical thing. And here we have kind of, I want to translate what they were talking about in the book to something that I can understand better because I'm too stupid to understand complicated sentences. So a feedback loop kind of allows us to control something that's insanely complicated, and I don't fully understand it. I don't understand how kind of, user demand works into something that fits into my head. Like, can I measure the number of tasks in a queue? Yes, let's start there. So I read a bunch of books about feedback systems, and there's a really good free book called Feedback Systems by a Swedish guy called Astrom, and it's a kind of university textbook. And he says that kind of in the book, the kind of core principle, if you throw away everything else, the core principle behind feedback is this kind of, you need to measure the kind of the error. You need to measure the difference between the actual performance and the desired performance, and then you need to make the system take a kind of correcting action on its own. If you do that, you have a feedback loop, and that's it. It doesn't need to be more complicated than that. So kind of going back to the example I had at the start, one thing that kind of happened to me recently, I was working on voice normalization because different text-to-speech voices speak at different volumes. If you want to create a dialogue like this, then it just sounds weird having different volumes. So there's known algorithms for voice normalizations. There's libraries for that. And I thought, well, if I just say, normalize and I use an existing library for that, that's done. And I released that stuff, and then somebody created something similar to this where there was just like one word there. And the system started blowing up. It turns that the voice normalization library I used cannot handle inputs that are less than 3 seconds long. There's not enough data to normalize. So I didn't know that. It wasn't documented anywhere. It's a third-party library. I could not have possibly known that. I was totally unexpected, and I was able to really prevent this problem from blowing up too badly by having a feedback system there. And the feedback system I had was like, I don't know what third-party libraries I'm going to put in. I don't understand them. But if shit keeps exploding, just roll back the release. I can measure exceptions in production. So there's a bunch of these deployment systems now that are amazing, where 5 years ago, maybe if you were Google or Facebook, you had this stuff, but it's totally commoditized now. You can use it as a single-person junior test assistant or test trainee, sorry. And basically, if this is an example on AWS, you create a deployment policy and you say, well, deploy this thing 10% every 10 minutes. And here, check for exceptions. This is an alarm you do. So that's a piece of code I had to implement. But that's it. It's basically giving us a feedback loop and saying, can you understand in some way what's wrong? If yes, we can create a feedback loop that prevents us from making stupid mistakes. And then it goes and deploys it like this, and you can see increasing. And if somebody starts causing something that causes exceptions, it just magically rolls it back so you can investigate it. And that's one of the key things that allows me as a junior test trainee to support like 250,000 people a month, making 1 million videos. And that's really important. Now, this is again a piece of detection that is very contextual, and that's the only thing we need to figure out. And this can go really crazy. I mean, for example, in theory, I'm not doing this, but for example, in theory, we could implement something that checks whether there was a drop in sales or a drop in conversion rates or something. So we don't need to understand what's causing a problem or why the user preferences have changed, but it can tell us, okay, you have a business bug in the system. It might not be a technical bug, but something you've done is causing, a new release to convert fewer people. Like, roll it back. And then we'll figure it out. Then we'll understand it. So, the feedback systems in general, these feedback loops mathematically and things like that, they tend to have 3 key benefits. And it's useful to think about which benefit you want before you start designing a feedback system. So the first key benefit is resilience to external influences. That was, I don't know what third-party libraries are going to do to me. I want to make a system resilient to that. And examples of that kind of stuff are, for example, a cruise control on a car. You can tell the car keep a constant speed, and then you might go downhill. The car will just see you going downhill and slow down the car. Or you might go uphill and the car will speed up. You can make a system resilient to external influences by doing that. The other thing that you can do is you can transform stuff that's non-linear, that's really difficult to understand, into a linear behavior that you can control and manage easier and figure it out. And this is where a lot of these human systems, when you put feedback loops around them, work. A lot of human process control, like Scrum tries to do, is about taking something that's non-linear and not predictable, having some kind of measurement there that's, a retrospective or something like that, and then feeding it back into the cycle to make the process predictable or to make the process controllable, more linear, easier to understand. And the third one that's really, really interesting once you start thinking about this and designing these systems is feedback loops allow us to make higher order decision making. So I want to show a vote of hands here. So just I'm going to ask you a silly question, and I want to see, if you think yes, raise your hand. If you think no, don't raise your hand. So in your opinion, does test-driven development lead to good design? Okay, about a quarter of the room. So the other people are not convinced. So for a long time I thought yes. For a long time I thought, you know, test-driven development is a really good way to lead to good design. But what I've realized is it's not. What it does is it is a way to lead away from bad design. And it's a feedback system that's telling you this unit test was so difficult to write that your system is rubbish. Go and build a better system. It doesn't tell you what a better system is. It's just kind of, this one is wrong, do something else. And from that perspective, you know, if you look at TDD as a kind of feedback loop, you don't need to be a super perfect expert in design. You don't need to be clairvoyant and see the future and everything. You just need to know that this one is shit, do something else. And then, you know, you try different things and one of them is going to work. And then you can apply your expertise, your knowledge and things like that to actually maybe create a good design, maybe not. So I think from that perspective, the key question is, when we do TDD, what kind of loop are we closing? And from that perspective, what are we measuring? You know, because you can measure a bunch of different things. Are you measuring the difficulty of writing tests? Or are you measuring how many tests are passing or failing? And you know, there's a whole perfectly valid argument around is TDD really kind of improving quality? Is it about testing? Is it not about testing and things like that? But I think a lot of the misunderstandings about TDD come from this whole thing where we can actually measure 20 different things with it. And if we measure different things with it, we get different feedback loops. If we measure, I don't know how many tests we wrote and what the code coverage is, then we get 100% code coverage with tests that are basically never failing because people skip testing and just return true. If we measure the difficulty of writing tests, we potentially have a way of coming up with good design. Similar to kind of, I think Eric Evans in domain-driven design talked about how all models are wrong, but kind of some models are more useful than other models. And he was talking about how a useful model is evolving symmetrically with the business. A small change in the business is a small change in the code. But there was no good guideline for how to create a good model. Just a bunch of heuristics, but there was a measurement there. It was like if you have too many corner cases, it's probably not a good model. So again, it's a way of looking at feedback, and that's kind of partially where spec by example comes in. If there's too many examples to describe something, this is a bad model. It's giving us feedback on a model, go and create a different model. And I think feedback loops like that are really, really, really powerful in system design because they allow us to create higher order thinking. Now, kind of this brings us to kind of the key question, like what do we measure here? How do we measure it and where do we measure it? Since the kind of invention of electronic components, because lots of electronic components are self-regulating systems and things like that, there was kind of this whole theory of control systems emerged and advanced and things like that. And there's really complicated stuff there. You look at diagrams like this, and there's kind of formulas with Greek letters and different colors and shit. But kind of essentially, a feedback mechanism has kind of 3 or 4 main components. And if you're designing a feedback mechanism, it's really useful to think through what those components would mean for you. So the kind of 4 main components for a feedback system are kind of the sensor. The sensor is measuring the difference between actual and desired performance. The sensor is the one measuring the error. In a case of TDD, then the question is our sensor about the difficulty of writing tests, or is our sensor about something else? Then the second thing they call is actuator. The actuator is the thing that's making an action. That's kind of creating the corrective action. And in a case of TDD, the actuator is the human. We need to kind of take some action, create better design. If we don't, TDD fails. And all these discussions we've had over the years where people have tried TDD but ended up with a shit system, that's because the actuator is not doing the work. And kind of then there's, the other thing is a communication loop. How do we send data from the sensor to the actuator? Because in a lot of these cases, the communication loop is at fault as well. Like, you put it in Jira, it disappears. And the last concept that's interesting to look at from a theoretical meta perspective here is something called feed-forward. Everybody knows feedback, kind of people don't know feed-forward. Feed-forward is kind of what we feed into the system for the first, to kind of get it going. And feed-forward is basically a way of saying we know some basic state. We know some initial state there. I don't have to let it run from zero. And for example, we've had like thousands of years of killing people with witchcraft, but then people figured out that these plants are really good for your blood pressure, so that if you have high blood pressure, you go to a doctor. A doctor doesn't put you in a feedback loop to measure you like for 2 months. They give you this pill. It's kind of feed-forward. And then you come back a week later, they see if you're improving or not, and then we have a feedback loop. So feed-forward is really, really useful if you have a good model, if you have data, if you have kind of stuff to justify the starting system. And this is where we get to kind of, one of my favorite feedback loops, kind of Scrum. We tried Scrum, but, it's too slow. We tried Scrum, but, the business people don't want to talk to us, or things like that. What people don't figure out is kind of, that's feedback. Scrum is a mirror. All Scrum is telling you is business people don't want to talk to you. It's up to you to kind of figure out the solution, but it's just telling you that every 2 weeks, so that you have some urgency to deal with that. Or, we tried Scrum, but our system is too difficult to maintain. Well, it's telling you that, and blaming Scrum for that is like, I got an extra kid recently, and whenever my wife was pregnant, I, get a bit of a kind of addition here as well. And then, I can stand on the scales and say, I have like, 10 kilos more than I had. And then next week I can do, I like have 10 kilos more than I had. But unless I do something about that, I can't blame the scales. I mean, it's pointless. So, and that's what people do with kind of Scrum all the time. So, Scrum has some concept of feed-forward. Scrum has some stuff that other people have tried, and it turned out it was a good idea in their context. Like, user stories has some stuff that people have tried. It was totally useless, but people keep doing it again, like writing user stories. But, and I think essentially when we're talking about the human system there and we're putting things, we need to come up with some basic rules for a feedback system. And that's kind of, all these 4 components. So if we have a loop without a feedback, that's not a feedback system. That's basically just running in circles. And people pretend they're doing iterations, but they're doing the same thing over and over again, and then they're complaining. So that's not a feedback cycle. We need to be able to measure the kind of problem. We need to be able to act on it. The other thing is, feedback without action is just horribly bad news. People become depressed. It's a problem with a lot of teams that are not empowered to act on feedback. Like business people don't want to talk to us, business people don't want to talk to us, business people don't want to talk to us. Well, the 3rd time you're not even going to try to talk to them again. You give up. So we need to be able to take this action. We need to, if we want to establish a feedback loop, we need to know who the actuator is. Maybe in this case, the actuator is somebody from the management. We need to kind of send them the message. We need to be able to measure the error again and things like that. And kind of the third thing that's kind of really, really important is if you have a dynamic system and you're trying to just manage it with feed-forward, the closest thing to that is basically astrology. It's like, Mars is in retrograde, your release will be successful. So you take this concept of astrology, you kind of, you start selling certificates on it, you scale it up, and what you get is a scaled astrology framework. So, wonderful. So now I'm going to kind of start wrapping things up here, and I just want to kind of give you a couple of different types of feedback systems you can design. So in physics, they talk about 3 different potential types of feedback systems you might want to design, different complexities, different ways of working with them, and kind of they are kind of an on-off system. That's one. That's a thermostat. So if the temperature is high enough, you kind of turn it off. If the temperature is not high enough, you turn it on. So the system can be kind of either on or off. It's like going to be electricity in Sweden this winter. We'll see. But it's kind of the benefit of this system, this type of system, is it's very simple. It doesn't take a lot to kind of put in. But if you look at kind of on-off with something like this, you might overshoot a lot. We might say we have 10 tasks in a queue, let's start another server. And then we have 7 tasks in a queue, let's start another server. And by the time we have 100 servers running, the tasks have all gone through. We need to start shutting down the servers and things like that. So an on-off system is creating oscillations and delays, potentially. And not necessarily always at the reference point. Then they have this thing called a proportional system. A proportional system would say, look, I have 20 tasks in a queue. I'm going to start 5 servers immediately. I'm not going to start one by one. Or I have 100 servers running. I'm not going to shut them down one by one. I'm going to kill half. So the response is proportional to the error. And the problem with these types of systems is they can keep things in range. They're really good for keeping things in range, but they usually can cause oscillations because we can still overshoot, we can still undershoot, we still need to predict like spikes and things like that. And then the third type is called a PID. It's proportionally integrative derivative controller, which has these 3 components to it. The derivative part is trying to predict the future. The integrative part is trying to average out the past. And the proportional is dealing with things at this very moment. And so, for example, in a server scaling system like this, we could say, oh, we had like an average load of 20 tasks last hour. So I'm not going to shut down 20 servers if I have them running because something's going to come in now, I'll have to ramp up. And it will say, like, from that past, how is the thing changing? I'm going to predict the future a bit. Are we expecting spikes? Are we not? And it will make things smooth. So the PID controller, the most complicated one, is making things smooth. That's the cruise control in a car. If it was not doing all these 3 things, you would be vomiting all the time. Because it was start, stop, start, stop, start, stop. It would keep you within the same average speed, but it would be really, really jerky. So the problem with that is the more you get into longer feedback cycles, the more the communication loop is delayed, the more it's important to predict the future and average out the past. With short feedback loops, the proportional thing is perfectly fine. And if you look at just the mathematics of it and what's intuitive to people, only this proportional reaction is intuitive to people, where you do something and it creates an equal reaction. So the other thing that is really interesting, apart from it not being intuitive, is in order to predict the future and average out the past, we need to have a really, really good model of it. Medicine can do that because they have thousands of years of data, what plants have killed whom and how that works on a large population. We cannot do that for programming. We don't have that data yet. We can pretend we do, but we don't. Especially for human dynamic systems. And one of the things that Astron talks in the book is, unless there are conservation laws there, unless you're working with physical properties that change slowly in normal distribution over time, mathematics gets insanely complicated. So my message here is really, speed back the loop so you can deal with the proportional aspect mostly, and then you don't have to predict the future and iron out the past. The faster the loop is, the less you have to do complex modeling, and even on human systems, we don't have the data to model it. So finally, there's some downsides to these systems, and I want to give you a couple of ideas just what to watch out for. Usually, they come down to 5 different things. One is we can cause stupid oscillations if we're not careful. So, for example, this summer we went to a hotel in the north of Sweden. There was a running shower there where you turn it on and then the running boiler, it warms up a bit. My son went in, turned it on hot. 2 minutes later, it was still cold. He turned it more on hot. Then scorching water came in, so, he jumped and screamed, and then he turned it back. But then it wasn't cooling immediately, so he turned it back more, and then it was ice cold, so he was screaming. So oscillations happen with systems like this. The other thing is we can create runaway processes. Runaway processes are things where the feedback loop is automating shit out of control. and people don't even see it like that. There's kind of another thing that they talk about in the book is that by creating a feedback cycle around two things, we couple them. And those two things might not necessarily should be coupled, and we can get unintended coupling. So if you put the thermostat on the outside instead of the inside, you've coupled the kind of your room temperature with the outside temperature, not the inside temperature. And then we can create like crazily hot inside because it's measuring the wrong thing. Because we've coupled two things that shouldn't be coupled. And another thing, kind of, if we're doing this thing for optimizations, we often get something that's just a local optimum. Feedback systems keep things stable. And people talk about, for example, using user feedback to develop good systems and to create a lovely thing. But you're not going to create something innovative with that. You're just going to keep the system stable. So sometimes we need a bit of feed forward. We need some experimentation, and kind of there's also the cost and complexity of measuring stuff that might not be trivial. And sometimes that causes problems. So for example, in 2019, I was flying through Amsterdam, and I got this lovely screen when I was checking in. They said, like, would you like to give us 55 euros to upgrade to product name? So somebody's doing user research there to get user feedback at scale. But the sensor is completely wrong. So at this point, I clicked no thanks. I assume most people did. I can't, like, maybe somebody really wanted to see what's going to happen and spend 55 euros. I didn't. But you can see, you can imagine, like, the Monday morning, a product manager came in and said, we looked at the data, this is a really bad feature. It's not. It's just kind of measuring completely the wrong thing. So the sensor was wrong. The message was wrong. In terms of runaway process, my favorite story is about the making of a fly. The making of a fly was a book that was written in 1992 and was totally like not important for 10 years or even more. And you can see kind of this is the book on Amazon. He was selling for £26 when I took a screenshot. And somewhere along the line, like in 2011, I think, Amazon allowed people to do algorithmic pricing and to compete on stuff that other people had, like third-party sellers. And there were immediately a couple of groups of sellers there. There were sellers who had really rare books. And with a really rare book, you don't even know what the market price is. So, you might try and price it high, you might price it low. You don't know if you're right or not. And this book was out of print by about, 10 years by that point. So it was very rare. There were another group of sellers that would basically apply these algorithms in a really clever way. They would build up a reputation. And they would have lots of 5-star reviews. And then they would think that if there's somebody else offering the book cheaper, but they don't have a good reputation, you would go and buy it from them. And what they did is usually they would create a pricing algorithm to say, we want to look at the cheapest one and we want to add 10%. And if they buy it from us, we'll just buy it from the cheapest guy and kind of sell it. So there was a professor in the US who he had a copy of this book, and he created an algorithm that basically said, this is a very rare book, and I have a bunch of rare books, so I'm going to offer it on the market, but if the second price is much higher than mine, I want to raise my price. So his algorithm would say, this guy is now showing up as soon as he published the book. These guys are now showing up. I'm going to kind of go 5% higher. And then the other guy said, now we are kind of, no longer 10% of the cheapest. We can't do the transaction profitably. Let's go a bit higher. And kind of in 2 days, it kind of reached these numbers. And kind of in 5 days, it reached kind of 23 million kind of competing. So that's an example of a runaway process, where everybody thinks they're doing what they're doing, but they've coupled stuff they shouldn't be coupling, and it's just going crazy. And my absolutely favorite example of a runaway process happened in 2010, where the US economy went bankrupt for about 10 minutes. and then recovered. And there's kind of Financial Times published this graph of kind of what happened to the US economy. That's absolutely amazing. There's kind of 1 trillion of value lost from stock market companies. Apple's stock temporarily jumped by more than 100 times. And what I think is incredibly kind of wonderful is Accidenture's stock went to less than 1 cent, and they were almost to get kicked out of the stock market because of that. And what had happened is there was this guy called Navinder Singh who was living with his parents in London, and he was kind of trading as an amateur trader, and he wrote an algorithm that would just send orders to the exchange and then cancel it a moment later if he doesn't think he's making money. And I don't know whether it was a bug or not, but he sent 19,000 orders to the stock exchange in a very short period of time. And because all the hedge funds and all the banks are now trading algorithmically, they saw somebody trying to sell so much different types of stocks, so everybody started selling like crazy. And then, other people started selling because these people started selling, and it was just a total runaway process for a bit, and then kind of, it recovered 10 minutes later. The guy's now in prison, kind of. The UK had to extradite him to the US for doing this. So that's kind of, I think, it in terms of please don't do this to your systems. So finally, 5 things to make this work. Really, if you try to make a feedback loop, make sure that you're measuring the right thing. That's really, really important. I think when I started looking at this more systematically, most of the stuff I was doing was measuring the wrong thing. And that wasn't giving me good feedback. So the second thing is watch out for kind of the sensor lying to you. Watch out for the data being transformed on the way from the sensor to the actuator. It's called sensor poisoning, but there's a ton of ways this could be like unreliable measurement. So, if we're measuring the, I don't know, Scrum, are we delivering more or not? Well, if you're measuring it with story points, who fucking cares? So, that's total sensor poisoning. Then watch out for like second order effects. There might be stuff hidden because you've coupled now 2 different pieces of your process that were not coupled before. And there might be unintended consequences to that. Look at kind of stuff where, if you're stuck at a local optimum, just, try something else, push it a bit, with feed-forward or mix the right amount of feed-forward, but don't copy somebody's process. You're not Spotify, don't copy their process. It's not that's total feed-forward. And really, unless you are incredibly good at maths and you know something that nobody else does, the best bet you have is to speed up the loop, because speeding up the loop avoids having complicated maths. You can deal with the proportional aspect of this. That's pretty much it. Thank you very much. So my blog is on gojko.net. If you're interested in kind of the tool I'm building, visit neraki.com. Thank you.